Today we are going to discuss about exponential distribution, which is a type of continuous distribution where a random variable x is in terms of exponent of theta, where theta is a parameter. We take probability density function since it's a continuous function where f of x is defined as theta into e to the power minus theta into x, where x varies from 0 to infinity and theta is greater than 0. As usual, let us calculate mean and variance using expectation method, where estimate of x is integration of x into probability density function, wherein the limits are 0 to infinity. Substitute the probability density function, and apply the limits. We get estimate of x as 1 by theta, that is the mean. Variance is calculated as estimate of x square minus mean square, which is integration of x square into e to the power minus theta x dx into theta, whose limits are from 0 to infinity, minus mean square. By using the product rule of integration and substituting the limits, that is 0 infinity, we get variance as 1 by theta square. We need to be careful while substituting the limits since we are dealing with 0 and infinity, which gives us quite a lot of trouble in mathematics. So now let us calculate the distribution function where probability of x less than or equal to x is going to be calculated. F of x is equals to f of y in dy integral over 0 to x. So we substitute f of y, that's our probability density function. So we get the distribution function as f of x is equals to 1 minus e to the power minus theta x. We move on to find the characteristic function 5x of t, which is estimate of e to the power itx, where I is complex variable. Substitute e to the power itx in your estimate and calculate the integral, which is theta into e to the power minus theta x plus itx, whose limits are from 0 to infinity. We get characteristic function as theta by 1 minus theta minus it. Next we move on for moment generating function, which is mx of t, which is estimate of e power tx. In the same way, calculate the integral over here too. Now we will substitute the limits 0 to infinity and get the result as theta by theta minus t. We have one more generating function called equivalent generating function, which is the differentiation of log of moment generating function with respect to t. So we will just substitute mx of t, that is theta by theta minus t, and find out the differentiation. We get that as differentiation of log of theta minus log of theta minus t. Well, k1 is defined as minus 1 by theta minus t into minus 1, where t is 0. So k1 is 1 by theta, that is the mean, which is called the first moment. Now we calculate the second moment by double differentiating. So we should get answer as 1 by theta square, since we know that second moment is variance. And there we go, we get 1 by theta square after substituting the limit as t equals to 0. We can also find moments using moment generating function itself as first differentiation of moment generating function, which you can actually tell that it's like the cumulant generating function k1. And the second differentiation will give us variance. We get mu2 prime as 2 by theta square. Mu2 is mu2 prime minus mu1 prime by whole square. So this is similar to estimate of x square minus variance square. So estimate of x square is given by mu2 prime, which we had calculated. Exponential distributions have a property called Memoryless Property, where a random variable x, which is defined by exponential of theta, and for all a greater than 0, probability of y less than equal to x, given that x is greater than or equal to a, is probability of x less than or equal to small x for all x and y is equals to x minus a. So here's a small proof of this property. Our probability density function, and then probability of y less than equal to x given that x is greater than equal to a is given as probability of y less than or equal to x intersection x greater than or equal to a, the probability of x greater than or equal to a. This is our conditional probability, which you would have come across before. So this is further simplified and we get it in terms of integration of f of x dx from a to x plus a divided by integration of f of x dx, where limits are a to infinity. Now we put in our probability density function, simplified further, theta get cancelled out, and we just have integration of e power minus theta in both numerator and denominator. Now after substituting the limits, we should get the answer in terms of our distribution function, which is like f of x, which we calculated at the start. F of x equals to probability of x less than equal to x is equals to 1 minus e power minus theta x. So this is what we should get. So if we get this, we have done the proof. We have got the proof for memoryless property. So here we go, we get our distribution function, which is p of x less than equal to x. Now we can also find characteristic function using Euler's formula, that is e power I theta is cis theta, that is cos theta plus I sin theta. So this is another way of calculating characteristic function, where you write estimate of e power I tx as estimate of cos tx plus I sin tx, which can be again written as estimate of cos tx plus I into estimate of sin tx. Put that into integration, you get integration of cos tx f of x dx integrated from 0 to infinity plus I into same integration limits sin tx f of x dx. We take theta common, and there is also one more term common after integration, e power theta minus theta x by theta square plus t square, and we now substitute the limits for the remaining term. As I said earlier, we need to be careful while substituting these limits. So we got two terms, and now we will we have denominator common, so we get characteristic function as theta square plus t square plus I theta t minus t square by theta square plus t square, which can be again simplified further to theta into I plus t minus t by I theta plus t. And finally we get characteristic function as theta by theta minus it, which is same that we got earlier. Since we write characteristic function as estimate of e power it, and we wrote e power it as in terms of cis theta, there's alternate way of solving this problem where you can isolate one term, that is estimate of cos tx, find the value separately, and similarly do for sin tx, and then combine those two values to get characteristic function of x. So meanwhile I'll tell you the applications where we use exponential distribution. So it is mainly used in reliability theory, reliability engineering, also during failure engineering. Most of the times it is used in radioactive materials, particle decays. If you are doing research in physics, you will know much more about this, the concept of half-life, etc. In physics, for gas at fixed temperature and pressure in uniform gravitational field, we use exponential function. It's also used in hydrology. So integration of cos tx e power minus theta x dx, where the limits are 0 to infinity, we get the term as theta by t square minus theta square by t square into integration of e power minus theta x cos tx dx, and limits are from 0 to infinity. So if you have some experience in integration, you would have encountered such type of problems where you get the question back in the right hand side of the equation. You take the question as common, that is, here we have the function cos tx e to the power minus theta x dx, limits from 0 to infinity. An indirect way of finding the integration. It's a trick method used in mathematics. So we get this integration term as theta by theta square plus t square. Similarly, we will find the value for integration of sin tx e to the power minus theta x, which we get as t by theta square plus t square. Then we will combine them as cis theta plus, so we will write theta into the integral value that we got for cos tx, and plus I theta into integral value which we got for sin tx. So characteristic function will get it in terms of theta and theta t and iota, which is theta by theta minus it. So we have found out this function using 3 methods, and we got the same answer every time. So we are consistent. Thank you.